Okay, thank you very much. So I would like to first thank the organizers for inviting me to lecture. It's really nice. This place is beautiful and the school looks really interesting. I'm sorry I arrived very late. Well, this is family constraints when you have little kids. So I'm sorry, but I will stay until Friday night, and so you are very welcome to meet me in the afternoon, ask questions and discuss. So I don't know, I've been thinking quite a lot about how I would organize these lectures, and I'm still not totally decided. So today I will for sure start with an introduction to the problem. But, well, I know it's the end of the school, so maybe you start to be a bit tired. And I also know that this, what I'm going to talk about is probably a bit off topic with respect to the rest of the lectures and maybe with respect to your background. So I thought to make these lectures very descriptive and try to give you the ideas and not to go too much into the details and the methods. But I'm open to change, so if after today you feel that it's too much speaking and too little calculations, you are welcome to give me feedback, and maybe tomorrow we could also do one calculation so that you see a little bit how it works. But for today, I will try to give you an overview of the kind of problems that we want to deal with in the field. So the idea, the organization, let's say, of the lectures is that I will discuss two toy models. That are somehow the Ising models of the field. So these are really the basic, the two most basic models that you start studying when you want to understand this kind of physics. And, well, I will introduce them. The reason I have to consider two is that they contain different ingredients in the. So, but just to give them names, the first one is called the P-spin glass, and it's basically the easiest spin glass. And the second one is called the perceptron. And it is a very, it's the simplest machine that you can meet when you study problems in machine learning. So it's interesting to make the connection between spin glasses and, let's say, machine learning and problems like that. So, okay, so these are the models, and what I want to discuss are three kind of dynamics in these models. The first one is the equilibrium dynamics. So we are all statistical physicists, I guess. So when we start doing statistical physics, the first thing we want to understand is the equilibrium properties of our system. But as we will see, these models, when you look at the equilibrium dynamics at low temperatures, you realize that you cannot equilibrate. So you can define and study the equilibrium dynamics, but you cannot reach equilibrium. So then, very naturally, what you need to study is out of equilibrium dynamics. And, well, when you go out of equilibrium, you can go out of equilibrium in many different ways. So I will study the simplest out of equilibrium dynamics, which is gradient descent from a random initial configuration. So basically, you prepare your system in a totally random state, which means infinite temperature, and then you quench it to 0 temperature, and you try to minimize the energy following the gradient. And well, the reason I'm going to do that is first because it's the simplest thing you can imagine, but also because that's what people do in many, many applications. For example, in machine learning, that's the standard way to try to train machines, is to basically initialize randomly and then do gradient descent. And well, the last thing I want to study is a combination of these two. So it's a dynamics in which first you equilibrate at temperature T, and then from there you take an equilibrium configuration at temperature T, and from there you do gradient descent. Okay, I will explain why this makes sense, why it's interesting to do that. But okay, this is basically the plan of what I want to discuss. And the focus, I mean, the interesting things that will control all this behavior are the existence in these systems of what is called the rough energy landscape, which means that when you look at the energy function at the Hamiltonian, this is typically, I mean, there is typically a cartoon like this where you have like energy and degrees of freedom, some configuration space, and your energy function contains many, many, many local minima at different levels of energy. And of course, this is a one-dimensional cartoon, but I mean, these things typically are very high-dimensional, so it's hard to sketch it. But so the important thing is that because of this roughness, you have metastability. So you have a lot of metastable states where the system can be trapped for a very, very long time before it can escape. And this is why it becomes difficult to equilibrate. Okay. Now, before I go into the details of this, I want to give you some examples of problems where these things appear. Also, to show you that this is a kind of interdisciplinary problem that has been studied from very different perspectives in statistical physics, but also in material science, computer science, biology, and so on. Okay. So the first example, so I will start from physics and I will move to other fields. So the first example is glasses. So when I say glasses, I mean window glasses, for example. So glasses are, well, glasses are everywhere, let's say. I mean, many, actually, probably most solids around us are glasses. But when you study material science or structure of matter, you typically think to solids as crystals. And the reason is that, well, if your solid is a crystal, you can do a lot of theory. You can understand the basic excitations of your solids that are maybe phonons or defects or grain boundaries and so on. While glasses are complicated, and so usually they are not. I mean, they are not part of the standard curriculum in undergraduate studies. for a good reason, because they are complicated. And why they are complicated? Because, okay, precisely because glasses are have this kind of property. So what are glasses? I mean, a glass like the one, that window there is a system of atoms. Okay, so you have a Hamiltonian, you have n atoms. In that case, it's silicon, and it's a mixture of silicon and oxygen, impurities and stuff like that. But anyway, you have n atoms, and your Hamiltonian, which is a function of the positions of the n atoms, is, you can, in the simplest case, you can consider as a sum of pair potentials. There can be molecules, so maybe it's the potential is not spherical and so on and so forth. But in the simplest case, you can think that you have spherical atoms and they are interacting with a pair potential. The pair potential is typically something like a Lennard-Jones, so something like that. You don't need to have attraction, so it can also be something like that. The important point is that there is a repulsive core, which is always there when you have atoms. Okay, so why we know that why do we know that this Hamiltonian function has this shape? Well, because when we prepare a glass, what we do is to start precisely, to do something like that. So we start at high temperature. We take our atoms and we mix them. So we have some high temperature melt. You mix all your things, you melt them, so you get a liquid. And if this is energy, let's call it energy. It's the average of the Hamiltonian. If this is energy, then you start somewhere here and you start cooling your system, okay? So you typically take your melt and you let it cool down. And what happens is that the energy will go down. And your system, the more it goes down and the more it becomes viscous, right? So that's what you see when you go to Murano and you see people like shaping glass. The glass goes down in temperature, it becomes cooler, and it becomes more and more viscous, so you can start giving it a shape. And then at some point it becomes so viscous that it becomes a solid. And typically what you observe there is a change in behavior. So you have some energy temperature curve for the liquid. And then at some point you get a different behavior for the glass. Now, the point is that if you do it again, but for example, you cool your glass at a different speed, you get a different curve. So for example, if you cool your glass very fast, then what you typically get is something like this. And if you cool very slow, then you get something like this, okay? So depending on the way you prepare your glass, you get a different energy. And this is the plot for energy, but for example, if you work at constant pressure, you can measure the specific volume. Well, let's call it volume. So if you go slow, your glass is denser. Yes?
H, you do not have any dynamical term in your other opinion?
Sorry, yes, I've always in mind classical systems. So yes, there is a dynamical term, but it's kind of trivial, so I don't, it's just the sum of, it's just the standard classical kinetic energy. But, well, we will discuss later the kind of dynamics that we can do, but I didn't put it explicitly because the system is classical, so I can separate the momenta and the positions. The momenta are Gaussians, and what matters is the positions.
And my second question about this is, when you plotted this, this seems to indicate that the glass is just a metastable phase, but aren't there a lot of study right now that shows that glasses are a state of matter just as liquid or solid, with a well-defined phase transition, in which case describing this curve might seem misleading in the sense that we have this definite phase transition between the two phases of matter.
Yeah, I mean, this is an open problem in the field. We don't know if there is a sharp phase transition or not, so there are different theories. I'm happy to discuss this later, but for sure, I mean, when you do experiments, you can change the cooling rate by orders of magnitude, and you get different results, okay? Then there is the question whether if you go infinitely slow, you would eventually get to a sharp phase transition with a well-defined glass phase, thermodynamic glass phase. But even if it's there, you cannot see it in experiments. It requires such a slow cooling that you don't reach it. So what you see in nature are always metastable glasses. So that was exactly the point I wanted to make, that glasses, at least the glasses that you meet in this room, are not equilibrium states. They are metastable states, and there are many different metastable states in the same system. So if you take that window glass, you bring it to high temperature, and then you cool it back, you will, depending on the way you cool, you will reach different minima in this potential, and this minima can trap the system for a long time, and basically you are stuck there when you are at low temperature. So this is an example where you have this kind of situation. You see it in experiments, and and then you see that it's interesting to consider, let's say, gradient descent or low temperature dynamics starting from high temperature.
You say that glass is pretty much like infinite viscosity, right?
Yes.
So then,
Well,
how about the photons? Are they like very strongly dissipative, like they don't?
So, okay, let's say viscosity. What I mean, in a glass, the viscosity is essentially too big to be measured. Then you can discuss if it's really infinite again or if it's finite but huge, because you always have defects and so on and so forth. But let's say it's infinite. There are phonons in glasses because I mean, if you look at large scales, it's an elastic solid. So you have phonons because of elasticity, essentially, and they propagate. There is an attenuation because they also scatter. The attenuation, well, and it's a long story, but yeah, you can study all these things. And you have other kind of excitations. I mean, it's...
Because I mean, the stronger viscosity, I think the stronger the attenuation of the moment.
Well, no, I think this is in the liquid phase.
Yes.
In the solid phase, you can think really that viscosity is infinite. So there is no viscosity, it's really solid, let's say. Or maybe it's, 10 to the whatever, big exponent in whatever units you want to measure it. So forget about viscosity, there is no viscous flow. What you get is really an elastic solid, but it's a disordered solid, so phonons will typically scatter on other things. And then you can... Okay. So this is my first example. Now the second example I want to discuss is related to this. It's what is called the jamming transition. So it's a very similar problem, except, so same potential as above, except that now the potential the pair potential has a finite range that we call L, for example. So it's something like this. This means that two particles, if you think to your system, you have some box, you have particles. Particles have size L, and if two particles are at distance bigger than L, they don't interact. There is zero interaction, zero force, zero energy. While if they are at distance smaller than L, then they repel. This is not usually the case in atomic glasses, because there is always some long-range tail in the force. But this is the case in many systems like colloids. So essentially mesoscopic or macroscopic systems. So you can think to colloids, or you can think to granular materials and other kind of materials. So colloids are typically mesoscopic particles that you put in a suspension, and because they are mesoscopic, you can think that, well, when they are far away, they don't see each other. And granular materials are like, I don't know, rice, coffee. So these are grains that are macroscopic, and, well, two coffee grains, if you put them far away, they will not interact, okay? So it's, of course, a model. I mean, you can always think that, for example, in colloids, there are hydrodynamic interactions because they are suspended in water, but in a first approximation, you can think that this is a good model. So what is the difference with respect to the previous case? That now you can have, when you go to low temperatures and you try to minimize the energy, you can have two situations. You can have a situation like this, where there is enough space for the particles to fit in the box. And when you increase the density, you can have a situation like this, where the particles are repelling each other. So here, essentially, when you are at zero temperature in a situation like this, nothing moves, and the pressure is zero. There is no pressure. This is a floppy system. So it's not really a solid, right? While this one, well, I'm not going to fill all the box, but you imagine that it's filled. This one is rigid, because if you try to compress it or if you try to shear it, there will be some energy cost to pay, okay? So when you take a system like this and you are at zero temperature and you compress it, typically what you see is a transition between this situation to this situation. And so here, let's say the potential energy is 0. Here the potential energy is positive. And you can also, well, okay, so this is also called unjammed in the literature. And this is called jammed. But the reason I'm mentioning this is that you can think to this as a constraint satisfaction problem. So you have some variables. Your variables are the positions of the particles. You have some constraint. The constraint is that each pair of particles should be sufficiently far apart that they don't interact. And the question is, can you fit the particles in the box in such a way that they don't interact, okay? So this is an example of what is called constraint satisfaction problem. And so depending on the density, here you can find the solution. So this case is called sat, or satisfiable. And this case, when the density is high enough, you cannot find the solution, so it's called unsatisfiable. And what, yes?
On thermodynamic sense,
Sorry?
I mean, on the thermodynamic sense and so on the speed, depending on the speed, if you take a jammed solid and you increase the volume, I guess it will take a lot of time to go from one mode to the other one, yes?
To one mode?
From the rigid system to the floppy one, because due to interaction, we will.
So, yeah, let's see. So, what happens in this kind of systems is that when you draw this cartoon, this is not the right way of representing it. I hope this can answer to your question, because you see that now, in this case, there is a new ingredient, which is that the energy can be 0. Here the energy is 0. And if you take this system and you take this particle and you displace it a little bit, the energy stays 0. So this means that there are regions that are flat, that are sitting at 0 energy. And so the correct way of drawing this cartoon is something like this. And well, and so on and so forth. So now the problem is similar to the previous one, except that there are these flat regions. And the question is, if you are sitting in a flat region, so of course you can move your particles a little bit, but can you, for example, rearrange the things in such a way that you can go here and then go here and then go everywhere? Or are you stuck in this one, and does it take a very, very long time to reach the other one?
I think my question in this sense was, can you go from one deep, which is at finite energy, to one flat region, because you have some energy barrier?
Yes.
And so you need enough energy fluctuations
Yes.
to be able to reach it, so that it can take a very long time. We can get some hysteresis curves and something like this in this model.
Yes. The answer is yes. All these kind of things happen, and that's going to be, I mean, part of what we are going to discuss. Just to add one thing, and then I take the question there. So, okay. Well, let me first take. There was another question.
Is it correct to think, it looks to me that there's some critical sphere density, and if you go above it, you can never satisfy this problem.
Yes, exactly. So that was the next thing, right? So there are two things that you can ask. The first thing is, well, exactly, is there a critical density such that there is no flat 0 energy region anymore? So I cannot fit the particles in the box without overlaps. So this is a question, and this would be something like, this is called a close packing configuration. So is there a density at which I reach the densest packing that I can make, and above that I need to have overlaps? So this is one question, but this is a static question, right? So this is a property of the energy function. Do I have flat regions or not? There is also another question, which is, can I, if I give you a dynamics, for example, this one, gradient, if I take gradient descent from a random configuration, so I start somewhere, I take an initial state at random, say here, I do gradient descent. Well, okay. let's say I take a random state, so for example this one, and I'm sitting here, I do gradient descent, I end up here, right? Now I do it again, and maybe I pick, by chance I pick this initial state, and then I go here. So here I found, in this case I found the packing, I found a zero energy configuration. In this case, I end up here. So the question is, can I, so if I take, for example, the average energy, if I repeat this many times and I do a histogram, and for example, I take the average energy, or I take the typical energy, whatever, do I see a phase transition when I increase density between a situation where I typically get the packing, if I repeat this many times, and the situation where I typically do not? Okay, so this is called, well, this is an algorithmic question, because now it's not a property of the landscape, it's a property of the algorithm. If my algorithm is very stupid, maybe there are flat regions, so there are packings, just I cannot find them, okay? So the question here would be, does my dynamics converge to a solution? Okay, and what we will see is that in these problems, very often, I mean, I would say generically, there are three phases. There is a phase, say at low density, where there are solutions and they are easy to find. So there are packings, and whatever algorithm you use, you find them. Then there is a very dense region where there are no packings. So whatever you do, even the smartest algorithm is not going to find any packing. But then there is an intermediate phase where there are packings, but they are hard to find because there are many other higher energy states that are not solutions. And if your algorithm is not very, very smart, it will typically get stuck into bad states. And then you get a transition between a phase where your algorithm typically finds solution to a phase where your algorithm typically does not. But this phase transition is not a static one, is a dynamic one, because if you change the algorithm, you get the transition at a different point. Is that clear? I mean, is that a good answer to the question? Okay.
I mean, when simulating dynamics, it makes sense to have different transitions depending on the algorithm, but in nature, I mean, if you take some colloids and you try to do the experiment, the algorithm won't matter if you are able to find it or not. You will get some, I mean, there is an algorithmic solution to the problem, and there is the real solution, which is the solution observed in nature. So,
well, nature, okay, there are two things. The first thing is that, I mean, the first thing is that this is interesting for non-natural application, if you want, that are typically found in, for example, in computer science or in machine learning when you want to optimize some function. But also in nature, I wouldn't say that there is one single dynamics in nature. It depends on what you do, because you are out of equilibrium. So if you have a colloid, you can decide how do you, I mean, you always, you know, when a system is out of equilibrium, it matters the way you prepare it, it matters the way you bring it to the final state. So you can, I don't know, if you have a colloid, you can change the solvent. For example, the solvent can be more or less viscous. This is a change in the dynamics. It will change the noise in your dynamics. So really, you can change, and this is what you see in glasses. I mean, if you change the cooling speed, you get different solutions.
So this approach is inherently numerical, right? There is no way you can solve this exactly.
Yes, there is, and that's my, I mean, there are toy models. I mean, of course, there is no way you can solve this example I gave you of three-dimensional or two-dimensional atoms in a box. This is not going to be solvable, but
It's like a nonlinear system. The method you solve nonlinear system with is precisely gradient descent. And there, the solution strongly depends also on your initial guesses.
yes, yes. So what I'm going to show is that I agree with you that the general problem is very hard, but there are cases where everything can be solved, and these are in these toy models, for example, you can really solve exactly the gradient descent dynamics. For example, starting from infinite temperature, or I mean, you can choose an ensemble of initial configurations, and then you can run your gradient descent, and you can solve the dynamics. Also, in the case of, in this kind of problems, you can solve them exactly if you go to infinite dimensions. So this is a two-dimensional problem, but you can do it in 3 dimensions, you can do it in 4 dimensions, 5, 6, 7, 8, 1 million. If you take the limit of infinite dimensions, which is of course very abstract, but for us, I think in statistical physics, it's a very natural limit because it's the limit where mean field usually becomes correct. You can do a mean field theory and you can solve, to some extent, this kind of problems. Okay.
Do you assume that the floppy systems have no dynamical terms in the Hamiltonian?
Yeah, yes, sorry. So this, yes, this was at, I mean, this was at the statements I made here were in the zero temperature limit. So there is no kinetic energy, let's say. You can add it back, and then you can discuss, like, for example, I mean, if you do gradient descent, you end up in this state. Now, if you put a little bit of temperature, for example, what happens? And you see, if you're in a situation like this, if you put a little bit of temperature, the system will explore this region, but jumping to the next one will take a very long time. So what you see, for example, in colloids, when they are dense enough, you have a situation like this, but when you put a little bit of temperature, they are going to vibrate, but they don't really diffuse. So yes, I mean, the statement, if you want, the distinction between SAT and unsat is at zero temperature one, because you have to see, because if you put temperature, there will always be a little bit of noise that will induce collisions, so you cannot tell if it's SAT or unsat. So yeah, exactly. So no, I agree. I mean, the metastability requires a little bit of temperature. So you have to discuss, when you put a little bit of temperature, do you go or do you get stuck? Okay, there is one last thing that I wanted to say on this that was kind of forgotten here, is the crystal. So, of course, I mean, this depends on the system you are considering, depends a lot on the system you are considering, but typically, the real ground state of a system of atoms is a crystal. So, where is the crystal in this picture? Well, the crystal is there. So if you take, this depends a lot on the system because the crystal can be, the type of crystal that you get depends on the shape of your molecules, on the amount of impurities, and so on and so forth. But in a typical case, if you take your liquid and you cool it down very slowly, you typically get a first order phase transition to the crystal, okay? So here there is a crystal state, and this is typically, this is a true first order transition. And in this case, the crystal is also important because typically the densest packing that you can construct is crystalline. So there will be, I mean, for example, in 2 dimensions, you know that the best packing you can make is an hexagonal one, so you do something like this. Right? So why I didn't mention the crystal up to this point? Well, because the crystal is typically, I mean, is a special state. It's separated to the liquid, from the liquid by a first order transition. So in this landscape, it's somewhere. So I don't know, for example, here there is the crystal. Now it depends if we are in the finite range or infinite range interaction case. But anyway, there is the crystal somewhere. But it is typically separated from the disordered regions by a big barrier. And so if you cool your system at a reasonable speed, I mean, then it depends a lot on the system, but in a window glass, you will not see the crystal, and the system basically has no time to go there. It just remains in the disordered part of the landscape, okay? So you can, usually the crystal is there, but you can consider it as a kind of separated state. Also, in the case of packing problems, this is an interesting thing. Thing is that in 2 dimensions, we know that the best crystal is this one. In 3 dimensions, we know that it's the FCC. We also have the best one in 4 dimensions, in 8 dimensions, and in 24 dimensions. These have been proven rigorously, and by the way, quite recently, there has been a field medal in mathematics for the proof of the fact that for the proof of the best crystal in 8 and 24 dimensions, recently, 2-3 years ago. But in all the other dimensions, we don't know which one is the best crystal. And, well, in low dimensions, like in 4, 5, 6, we have good guesses. I mean, if you can more or less enumerate the possible crystals and you can find the best ones. But when you go to high dimensions, say above 150, something like that, so above 150 dimensions, we don't know good packings, and even numerically, it becomes hard to find good packings. And so the problem of what's the best packing in large dimensions is open. And there are even people who think that maybe crystals are not denser than disordered packings in large dimensions. And this might seem a totally academic problem. You would say, okay, why should I care about the best packing in 1 million space dimensions? Actually, it's not a purely academic problem. I mean, it's a very interesting academic problem, but it's also very interesting for applications because the problem of packing spheres in a volume is related to the problem of error correction. So the idea is that this is a little digression that I will close immediately, but the idea is, the rough idea is that if you want to send a message through a channel, a message, you can think to a message as a point in a space, and if your message is a signal, you can discretize your signal. Each point each discrete time is a coordinate. So typically a signal is very high dimensional. So you have a point in very high dimension. You send it through a channel. The point gets corrupted by noise, so it moves a little bit to another point. And so the question is how many signals you can pack in your space of signals such that when they get corrupted, they don't get mixed, okay? So this becomes a packing problem in high dimensions. I'm happy to discuss this in the afternoon if you want. So many people are interested in being able to pack spheres in high dimensions. So there are mathematicians working on it, there are computer scientists working on it, and well, it's an open problem. I mean, the best packings we have are not very good. I mean, we know that there must be better ones, but we cannot find them. So anyway, so this was a digression to explain that the crystal is there, but in the cases I'm interested in, it's very hard to reach, so we can forget about it and just discuss the disordered states. We have a break in 4 minutes, right? So maybe, yes, I'm thinking whether I start another thing or not. Well, yes, let me say relatively quickly one more thing, I mean, 2 more things. In 5 minutes should be enough, and then we can take a break. So these things that I started from the physics side, so I was speaking of particles, but these kind of problems are very general, and so in computer science, for example, this problem here of minimizing the energy of some degree of freedom is very common, and these are called optimization problems. And I just wanted to give you one example that is a very famous one, and was also one of the first that were studied by the statistical physicists, that is called the traveling salesman problem. So it's a problem where you have cities. Each city is a point. So you give an index I to each city, I equal 1, 2, 3, and so on. And you have a cost to go from city I to city J, and you call it W. And this can be, I don't know, the cost of the train ticket, for example. And so you are a traveling salesman, and you have to visit all the cities. And what you want to do is to find a path. So for example, you start from city 1, 2, 3, 4, 5. You go to city 5. Then from 5 you go to 3. Then you go to 2, and so on and so forth. And then you go to 4. So you visited all of them. Now if you, for a given path, so a path is a sequence of indices, right? I1, I2, I3, In, if you have n cities. So it's a permutation of the cities. And so each path has a cost. We will call the cost h. And this is just the sum of w ik plus 1, sum over k, from 1 to n minus 1. Right? So your problem, if you want to optimize your cost, is to find the permutation of the cities that give you the minimal cost, okay? And you see that this is a kind of a similar problem. You have a function of some coordinates. Here the coordinates are is the permutation. The degree of freedom is the permutation of the points. So you have a function and you want to find low energy configurations. And well, you can show that this problem behaves very similar to a glass, and there are actually many problems like this that behave in the similar way. And well, you can ask questions. I mean, there are questions that are typically studied in computer science, which are, well, the first one is, can I find the ground state? But let's say a less ambitious question that you can ask is, is there a state with energy smaller than some threshold. So, for example, you have a certain budget, and you say, okay, I don't care about finding the best possible path. I just want to find one that satisfies my budget. And you see that the problem in all these cases, the difficulty comes from the fact that the space of possible configurations is very big. So if you have n cities, then you typically have, I mean, if you have n cities, you have n factorial permutations. So you cannot just, if n is large, you cannot just solve the problem by enumerating all the possibilities and checking them. Okay, so you have to find some algorithm that will output low energy configurations for you. Can I say one more thing before the break? So the last example I wanted to give you is that of constraint satisfaction problems. So what I just wanted to say is that you can generalize this kind of problem where you have now, you have an energy function that has 0 energy states, and you want to know, can I find them? So a typical problem that people in computer science like is the problem of graph coloring. So you have a graph, I don't know, whatever, something like this. You have a graph, you have colors, blue, I don't know, green and red. And what you have to do, you have to put on each node of the graph a color in such a way that the nodes that are connected have different colors. So for example, if you put here a blue, then this has to be either green or red, so I can put green, for example. Here I can also put green. Here I can put blue again. Now this is blue, this is green, so this one has to be red, right? So this is a solution. How do I write this in the form of this kind of problem? Well, again, I introduce a Hamiltonian, which is the sum over links. So I give an index I to the nodes. Then I sum over all nodes I and j that are connected by a link in my graph. And then on each node, I put a variable, sigma I. Sigma I is a Potts spin that takes 3 different states, 1 for color blue, 2 for color red, and 3 for green. And then here I just put a delta of sigma I, sigma j. So this is an antiferromagnetic Potts model in physics literature, in physics notation. And again, if the Hamiltonian is equal to 0, this means that I found a configuration of colors that satisfies this constraint that colors connected by a link should be different. So my problem is sat. If the Hamiltonian is positive, then my problem is unsat. Let's say the ground state, okay? Okay, so now you have the full picture. On this side, you have physics. On this side, you have computer science. But you see that the problems are quite similar, and it's all about understanding low energy states of some cost function, some Hamiltonian, and and how can we find them. So we can take a break. In the next hour, I wanted to show one more application, and then we can start discussing the toy models.
Just a quick question. For the purposes of physics, is it ever possible to use a cost function that has a negative number? So it's not really a cost function, it's something
Yes, I mean, the important point is that it's bounded from below. Then you can shift it. I mean, the value 0 is not special. You know, you can always shift the energy, so you can choose. The important point is that there is a minimum value such that when the cost function is equal to the minimum, it means that your constraints are satisfied. So if I subtract 1 here, it's okay.
Other questions before the break? No? Okay, so let's take the second one.
Typical problem is supervised learning. So in supervised learning, you are given some data that are points in a space. And for each data, you have a label, y. Oops. So you have pairs of inputs, input data, for example, an image, and labels, for example, cat and dog. And let's say that you have capital M data. So what do you want to do? Well, you want to basically fit this. So you want to learn a function G that depends on some parameters theta, right? So you want this function, if you show to this function an input, you want this function to output the probability that the label is a certain label. So to make it simple, let's assume that the label is 0 or 1. I don't know why it's doing that, but so let's say 0 is dog and 1 is cat. So what you want is, if you show an image to your function, you want your function to give you a number that is the probability, for example, that the label is 1, okay? So, and this function G depends on some parameters. And so what do you want to do so you want to learn these parameters to obtain the best possible fit. So what you're going to do, you're going to introduce what is called the loss function that depends on theta. And this is an average over the data points that you have in your, this is called the training set. I mean, I guess these days, I guess all of you know this by heart, but just to repeat it. So you define this loss where there is a certain function E, this is an E, that depends on the true label of your point and the predicted label. The predicted label is the function G. And this gives you a measure of the quality of the prediction. So just to be concrete, this function can be what is called the cross entropy. Where E, the error, let's say, between the true label and the predicted label is something like minus y log y predicted minus 1 minus y log, sorry, well, this is 1 minus y, sorry, it's a bit small, I hope from the back you can see, probably not. Let's write it again. I'll try to make it a bit bigger. So this is minus y log yp minus 1 minus y log. Yes, so this is a number in 0, 1. This is just an example. I mean, you can formulate this in many different ways, but This is one way. So I give you inputs, images, for example. For each input, I give you a label. So 0 is cat, 1 is dog. Then you have this function, g. So the function g to a given input associates a real number that we are going to, in 0, 1, that we interpret as the probability of the image being a dog, so label being 1. And so you see, if you take the cross entropy function, if the true label is 0, so then this is 0, and so and this is 1, so what you want to do is to if you try to minimize this function, what you're here you have minus log of 1 minus y, so you want y to be as close to 0 as possible, right? And the other way around. So then what you do is you take your training data. For each data point, you compute this probability that the label is 1. You compare it with the true label, and then you want to minimize this object over the parameters theta that you have in your function. Is that okay? I mean, you can formulate it in many different ways, but in the end, what you get is a sum over data of something. And well, this function, you can see, for example, in this example, this function is equal to 0 if the data is perfectly classified, right? So if for each input the function g can give you the correct label, then this is 0. And so, and well, you can also see that the cross entropy is positive. So in the end, this function L looks like, so if this is the space of theta and this is the loss, this looks like the kind of things I drew before. So when it is 0, when the loss is 0, it means that all your data points have been correctly classified, okay? The training set. So, yes, g is a function that you decide. So you want to, you decide a class of functions with some parameters, and then you want to find the best parameters in that class. So this is very similar to this kind of problems. You have your loss function that has 0 regions where it's 0, that are the regions where your machine has perfectly learned the association between image of cat and label of cat on the training set. And you have regions where some data in the training set are not well classified. The difference, I mean, if you want the additional ingredient that you have, and okay, well, and typically, sorry, I forgot to mention, typically what you want to do, what people do to get a good machine is to use gradient descent. So they do something like this. So you start from some point that you take at random, and then you follow the gradient to reach the best solution. The additional ingredient that you have in this case is that now you don't want just to satisfy the constraints. So if you want the training data give you some constraints that your machine has to satisfy. So you want to classify the training set in the best possible way. But then what you want on top of that is that your machine is able to generalize to new data. So there is an additional requirement that is called generalization. So what you typically do is that you generate new data, okay, and you check what is the average error that you make on the new data, okay? So, well, I'm not going to give you the mathematical definition, but I think you can guess it. So now this is a new ingredient because it's not something that is a priori contained in the loss landscape. Okay, so you have this loss landscape that is a function of these parameters theta that you want to learn. You try to minimize the loss, but the loss depends only on the training data. In principle, now you want to show new data to the machine, and in principle, the machine has not seen them, so they are not in the loss. And so the question is, can you guess something about the generalization properties from the loss? And I will not have time to discuss this a lot, but already in the toy model that I will introduce, the perceptron, there is the possibility to play with this and to study generalization. I can give you references. And now, I mean, these days there is a big discussion on whether, for example, I mean, what is for example, quite clear is that these new machines, I mean, these deep networks that work well in doing many tasks, they typically work in a regime where they can reach these flat regions. So they typically classify perfectly the training data. So there are a lot of parameters. So there are enough parameters that you can solve all the constraints. And so you are typically, if you want, in this low density regime, if you think in terms of particles, where there are few constraints and many degrees of freedom. So you typically reach these valleys. And then there is the question, I mean, there is a debate on whether the fact that, for example, that in order to maximize generalization, maybe you want your machine to be in the biggest of such valleys. Okay, so maybe there are valleys that are smaller, others that are bigger, and the performance of your machine in generalization depend on where you are going. But okay, there is a debate. So if you want to follow this debate, if you are interested, I can give you references. But I wanted to mention it because it's connected to the... Okay. Well, there is a last example that I could make, but I will skip it because I think it's also boring to give too many examples. So now let's go to the topic of the lecture. So so the problem we have, I hope at this point you agree that, I mean, it's a problem that is interesting for many different applications, is that we have some function h of some degrees of freedom x that we want to minimize somehow. This function, so this can be the potential energy for particle systems, can be this cost function there, can be the loss function. The important thing is that this function has many minima, and Well, in some cases, this function also depends on some disorder. So, well, there is some disorder in the problem. So, for example, in the particle case, this is just the potential energy, so there is no disorder, okay? You just have particle positions, you have a function that gives you the pair potential, and that's it. In the case of the machine learning here, there are some degrees of freedom that are the theta. So these are the degrees of freedom that you want to minimize. But there is also something else, which is the input data, okay? So this, if you take two different realizations of this problem, you will have different input data. And so you can call this a disorder. Or for example, in the case of the coloring here, the variables that you want to minimize are the sigma, the colors, but then there is an input, which is the graph, right? So the graph is going to be the disorder in your problem. So the disorder can be the graph, it can be the training set, or other things. So what I will call disorder is whatever you need to specify your problem. And then there are some degrees of freedom that are the ones you want to minimize. We will come back on the disorder, but the point I wanted to make here is only that you don't need disorder to have this kind of shape in your landscape. So if you take particles, they will just do it by themselves because there are many possible ways to pack the particles in space.
If this is a space-like disorder, would you have some, well, effects like localization of particles, etc., because of
Yes. Yes.
localization?
Well, I'm staying in the classical world, so I don't have Anderson localization, but yes, in principle, if you add quantum. Yes, but I'm not considering waves. I'm just taking. But yes, so you can have localization. Actually, the glass transition is a kind of localization in the sense that if you look to one particle, in the liquid, the particle can diffuse, and in the glass, the particle is kind of stuck and it cannot diffuse. So it's a kind of localization, yes. Okay, so now we have this function, and we want to minimize it. What do we do? So, so we would like to have some general algorithm to solve these problems. And so what people did in 1983, there is a paper by Kirkpatrick, Gelat and Vecchi, I think. So there is a paper that introduced the idea of simulated annealing. And, well, it's a paper that has, I don't know, 10,000 citations for what it matters. But anyway, it's a paper that had a huge impact on the field. And the idea was basically to take inspiration from glasses. So in glasses, what we do is we start at high temperature and then we go down at a certain speed. And we know that if we go slower, we can go lower. If we go even slower, we can go even lower. Can we reach the ground state or not? So the idea of simulated annealing was to do in the computer what nature does when you cool a glass. So start from a random configuration and then do Monte Carlo dynamics and reduce the temperature at a certain speed. Let's say cooling rate. Well, now the problem is that studying this kind of dynamics is a little bit complicated because Monte Carlo is, well, I mean, doing analytics on discrete time is not very, very simple. So what we are going to do is to study a version of a continuous version of simulated annealing. So, but okay, I will give you the details in a second. So the last thing I wanted to say before giving you the details is why I said I wanted to study three things. The first one was gradient descent. No, sorry, the first one was equilibrium, right? So equilibrium is a special case of simulated annealing. It's the case where the cooling rate goes to 0, right? If I start at high temperature and I cool my system infinitely slowly, in principle, at each temperature I reach equilibrium, and then I should go to the ground state. The second limit I wanted to study was gradient descent. So gradient descent is actually the opposite limit, is the limit where the cooling rate is infinite. If I go very fast, I'm basically, I mean, the noise is not very important. I'm basically going instantaneously to 0 temperature, and then I'm following the gradient, okay? And the third limit, the third case I wanted to study was first equilibrate at a certain temperature T, then do gradient descent. So why do I want to do this? Because this is actually a good approximation to simulated annealing in the following sense. If you look, well, let's draw it here. If you look to the relaxation time, let's call it equilibration time of your system as a function of temperature, what you expect is that it's going to do something like this, okay? The lower is the temperature, the more time it takes to reach equilibrium. That makes sense. So if you run a dynamics and you lower the temperature at a certain speed, you have a characteristic time scale, which is basically something like 1 over the cooling rate. This is not in the right units, but you can make it to have the dimension of a time. So you are cooling at a certain speed, and so you have two situations. You have a situation where at high temperature, you are able, I mean, the equilibration time is shorter than the time over which temperature is changing. And so this is the situation like here at high temperatures, where more or less whatever the cooling speed you have, you are always following the equilibrium curve. Okay, so this means that in this region, more or less, you can equilibrate. So the details of your dynamics doesn't really matter, you are just equilibrating. But then at some point, the equilibration time becomes bigger than the typical time scale over which temperature changes. So the system is not able to follow adiabatically the temperature change. It's going out of equilibrium. And if you want to make an approximation, you can think that, well, at this point, you are essentially in a regime where you are following the gradient. It's like if you were effectively at very, very low temperature with respect to the time it takes to equilibrate. And so it's an approximation. It's not correct, but it's a decent approximation. In this regime, you can think that you are essentially doing gradient descent. So if you want, you are approximating a complex annealing that you have here by two processes. First, you equilibrate down to some temperature T, that is more or less this temperature here. And from there, you do gradient descent to the nearest energy minimum, okay? So this scheme is a way to more or less rationalize what you get in simulated annealing. Then you can always try to do better by taking into account that you are doing it at a finite speed and so on. Okay? Now, okay. Sorry, I'm thinking what I do next. I will. Okay. So as I said at the beginning, I want to show you what happens in these toy models when you do this kind of dynamics. So maybe let me now introduce the toy models. The first one. Yes.
When you talk to people doing some quantum simulation, quantum simulation seems to be a powerful engine to solve such problems.
Mm-hmm.
So what does it, how does it improve all these kind of strategies used with quantum-like
Yeah.
simulation models?
So the quantum analog of simulated annealing is called quantum annealing. And the idea is the following, that you take your Hamiltonian. So let's say you have spins. So you want to solve, you want to find the ground state of this Hamiltonian. So what you do is, okay, you say these are classical spins. Let's say I go to the sigma z. I take the computational basis to be the z direction. And then you add to this some, for example, a transverse field. So now you have your quantum Hamiltonian that is a combination of these two. You work at 0 temperature, for example, and you say, okay, now I make this transverse field time dependent, and I start at initial time, I start with a very large transverse field. If I start with a very large transverse field, then this term is essentially small, you can forget it. And so all the spins are going to be polarized in the x direction, which means that you're in the z representation, your state is completely delocalized. So this is like taking a random state, a totally random state in the z direction. And then you say, okay, now I reduce my transverse field. I do the quantum dynamics. If the system is adiabatic, I will stay in the ground state. So I can look as a function of the transverse field to the Hamiltonian. At very large transverse field, I get this polarized state. And then, if I'm lucky, maybe I will end up, when I reduce my transverse field, if I can stay in the ground state, I will end up in the ground state at 0. When I send the transverse field to 0, I will end up in the ground state of H. That's the idea. Now, well, there are problems where you can show that it works well. For the kind of glassy problems I will discuss, there is a problem. I mean, of course, what can go wrong here is that you can have a level crossing. So if you have, imagine that there is an excited state here that is something like this. So your classical ground state is more or less, evolving like this, and your polarized X state is going like this, and they cross, and here you have a gap. So now you know that if you do quantum dynamics at 0 temperature and there is a small gap, you have a Landau-Zener thing, and you will, in order to stay in the ground state, you have to go slower than the gap. And the problem is that the gap in this kind of problems is exponentially small in the size of the system. So this has been shown, and I can give you references. And so you need to be exponentially slow in the system size to stay in the ground state. Otherwise, you end up. So you can ask very similar questions. So if you do your annealing at a finite speed, what you expect in the thermodynamic limit is that you are going to reach some state. So if you go a bit slower, you are going to reach a bit lower state, and so on and so forth. But in order to reach the ground state, you need to go exponentially slow in system size. And so the question is exactly the same as here, with transverse field playing the role of temperature. And so you can ask, for example, here there is a prefactor. So the time it takes for quantum annealing is given by exponential of n with the prefactor. We will see that thermal annealing has the same property, so there will be some thermal prefactor. Which one is smaller, for example? So you could hope that the quantum annealing maybe improves the prefactor. And well, it's an open problem, actually. There are cases where it has been shown. I also worked a little bit on it. So I have a few papers on that where you can show that, the two prefactors are essentially of the same order. There are cases where it seems to be better, so it depends on the system. But yes, in principle, you can generalize simulated annealing to a more complicated annealing where, for example, you can say, okay, if I have a quantum system, I can have temperature and transverse field. I can start anywhere at high temperature and transverse field, and I can do a path. In the end, I want to end up at 0 temperature and 0 transverse field, but I can arrive there in many ways. And so similarly, there is the idea that you can, here you're doing it with quantum fluctuations, but you can add other kind of fluctuations to your system. So even in the space of classical Hamiltonians, you can add some degree of freedom and remove it progressively, and so you can do annealing. So thermal annealing is just the simplest idea. Okay, okay, let me introduce my model, and then I think I will stop, and next time we can analyze it. So the model, okay, so this is the first toy model. And well, the reason why it's interesting, I think, is that it answers to the question that was made before. So this is a case where you can solve everything, and you can understand what's going on. And then you can see that the same kind of phenomena are there in more complex models. So it's a good toy model for that reason. How does it work? Well, it's very easy. You take a sphere. So we want to work with, in order to do gradient descent, we want to have continuous variables. So we take a sphere, and we take a vector sigma on the sphere. So sigma is a vector with n components, and there is a constraint that the square of sigma is equal to n. The reason for the n is that just this means that typically these components are going to be of order 1, okay? So this vector sigma is a vector on the sphere of radius square root of n in n dimensions, okay? I have n of them. And on this sphere, I want to define a Hamiltonian. And the way I will do it, okay, I will first introduce a function HP. So this is going to be the sum over groups of p spins, sorry, I1 smaller than I2 smaller than IP of J I1 IP sigma I1 sigma IP. So what's this? So I'm just taking groups of P spins, that's why it's called P spin, and I make them interact. So for P equal 2, this is the usual two-spin interaction, right? Okay. For P equal 3, I get something like this. For P equal 4, I get 4, and so on and so forth. So this is a function, and then the couplings, J, I will take J, the J I1 IP. So first of all, you as usual, the coupling of I to J and J to I is symmetric. So that's why I only sum over I smaller than J. So J I1 IP is going to be the same for any permutation of the indices. And I'm going to assume that these are Gaussian with zero mean, so this means Gaussian, with zero mean and variance P factorial divided by n to the P minus 1, maybe with a factor 2, I don't remember, yes, we put a factor 2. So this is the mean, and this is the variance. So, you know, for a Gaussian, you have only to give the mean and the variance. And
the same for all the possible couplings. Where is the indices dependent?
sorry, so each of the J, for each choice of indices, each of the J is an independent random variable with this mean and this variance. So for example, in the case of two spins, I take, I don't know, I have J12 is a Gaussian variable with zero mean and variance, and J23 is another variable independent from that, and so on and so forth.
Is it novel, this line of, well, SYK model and other like this, which also come from the random spin models with K-spin?
Yes, yes, this is an SYK model. I mean, if the sigma are fermions, this is SYK. So yes, maybe in this community is but well, yeah, in the spin glass community it's called the P-spin because it's there since the 80s, and it was called P-spin at the time. So the general Hamiltonian of my P-spin is going to be the sum over P from 0 to infinity of square root of alpha P times HP, where alpha P are coefficients, and the HP, each HP contains P-body interactions, and they are independent. So for example, the couplings of H2 are random Gaussian, the couplings of H3 are also random Gaussian, and they are independent. So now a little exercise for you. that you can do this afternoon if you have time is to convince you of the following thing, that if you fix the configuration of the spins, so if I fix sigma, so I take one given point on this sphere, then h of sigma is a Gaussian. So then for each sigma, if I take another configuration, let's call it tau. So here I have the energy of this one and I have the energy of this one and any other. If they are all Gaussian, then what I need to specify to get the statistics of this function is the mean and the covariance, right? And so the exercise for you is to show this, to show that the mean of h is equal to 0. So this over bar here is the mean over the j, okay? For a fixed sigma. So you fix the sigma and you take the average over j. And the third exercise is to show that the covariance between h of sigma and h of tau for any pair sigma tau is given by a function f of q sigma tau, where q is the scalar product of sigma and tau divided by n, and f of q is a function given by sum f of q is given by the sum over p of alpha p q to the p. So you can do it. It's easy, and I'm happy to discuss it. I think it's good if you try to do it because it helps understanding the definition of the model. There is a 1/2 here that I forgot, but it's just convention. So what is the important? So why this is a good toy model? Because you see, well, this is the Hamiltonian, the cost function, the Hamiltonian function is defined on this sphere is a random function. So it's going to be rough. You expect that it's going to be rough because it's a random function. But also it has a property that if you look to two configurations and you look to the covariance of the Hamiltonian, this is a function of the distance of the configuration. Okay, this is the scalar product is essentially distance. So if the two configurations are very similar, this function is going to be bigger, right? Because if you put q equal to 1, q equal 1 is when they are perfectly aligned. This is a monotonically, well, okay. The alpha p, I forgot to mention that, well, the alpha p are going to be positive, okay? These are positive numbers. So if the alpha p are positive, this is a monotonically growing function of q. So if the two configurations are very close, then the covariance of the two Hamiltonians is high, so they are similar. If the two configurations are very far, if they are, for example, if they are orthogonal, which is the farthest you can be on the sphere, well, you can be on the other side, but there is a symmetry here. So anyway, if they are orthogonal, q is equal to 0, and so the covariance is 0, which means that the two functions are essentially, the two Hamiltonians of two configurations here and here are essentially uncorrelated. So this is a simple model because h is Gaussian. The fact that h is Gaussian means we can hope to do calculations, and we can do many of them. But also, it's kind of smooth. Okay, this is a requirement of smoothness, because if you take just random Gaussians, totally uncorrelated, so if you take this covariance to be 0, then it's not a very physical model, because if you take a point, it will have a certain Hamiltonian. If you take a point very close by, it will have a totally different Hamiltonian, which is not what you want to have in a system with kind of local interactions, right? So this requirement, this property, means that it's a minimal requirement that the covariance of two Hamiltonians depends only on the distance of two configurations, but it gives you a kind of smooth function, okay? So that's the model we are going to study. I stop here. You can, yes?
How is it possible to,
Sorry?
how is it possible to define HP if P is larger than N?
Yes, sorry. Well, here it's always, I'm assuming that somehow N is going to infinity at fixed P. So I always want to take the thermodynamic limit first. And I mean, in the end, I write it formally as a sum to infinity, but in practice, for what we need to do, it's enough to keep P, I don't know. Typically, we take mixtures of two values of P. So there are only two, I don't know, you mix 2 and 3 body interactions, or 3 and 4. But yes, that's a good point. I mean, I'm assuming that P is finite and N is going to infinity. And well, this sum is cut at some value that depends on N.
But to do this exercise, do we need to assume that N goes to infinity, or is it true?
No, this is actually true. I mean, if you modulo, I mean, this cutoff on P, so if you fix P, yes, if you assume that alpha is 0 for P bigger than N or something like that, this holds for finite N.
Very good. Other questions?
So in this model, there is no notion of dimension of space.
Exactly. It's a mean field model. So you can think that it's a kind of infinite. So you can take a model on the d-dimensional lattice, and if you send d to infinity, it will converge to something like this. So it's the mean field case, and that's why we can solve it.
Okay, well, so is there a motivation for this strange constraint?
The spherical? No, it's just, I mean, if you take, okay, if you can do the Ising version of this, where the spins are Ising, then this constraint is automatically satisfied, and basically you are just taking, a subset of the sphere, which is the hypercube. The problem is that, first of all, okay, the thermodynamics is a bit more complicated for Ising because you have sums instead of integrals. Here everything will be done in terms of Gaussian integrals. In the Ising case, you have to work a bit more, but but then when you want to do the dynamics with Ising spins, you have to, it's a discrete, then it's a Markov chain. You have to, it's harder. In this case, it's essentially like the Ising, but you can do Langevin dynamics because these are continuous variables. And this constraints is needed because otherwise this is it's unbounded, right? Like in the two, if you have sigma I, sigma j, and you put, and jij is a random matrix, you have directions where the Hamiltonian is growing in this direction. So you put it on the sphere just to avoid explosion. Another way would be to add, sometimes people do the same, but instead of this, they put like a double well potential on each spin. It's just a bit more complicated if you do that. This is really the easiest case because everything is Gaussian, plus this constraint that is going to be implemented automatically by a Lagrange multiplier, and that's it. So it's really, that's the easiest model you can imagine.